and find some very interesting videos to show the undergrad students. And and I find that when the liquid gallium was flowing on the hands, when they lift the hands, they lift a lot of gray materials, and
correct.
I know that these are actually the 2D materials, just like the again when they found the exfoliated graphite was
Correct.
actually the graphene. So I
Yeah,
think
exactly.
it's very interesting, and I noticed your paper. So I think that is very interesting work, and I noticed you have published more on this area. So I was thinking, because I came from inorganic synthesis background, and I was doing some catalysis right now. So I was thinking that maybe we can do something on the basis of your science work, and I was trying to do that. So I noticed that the water system has some limitation, and I noticed that there is a projection at the end of your science paper that maybe the high boiling point solvent can be used to synthesize many other 2D oxides. I was trying from that time and find some new problems and try to solve it. That was the starting point for my lab papers.
Good, very nice, fantastic. Actually, I was between me and you, I was a reviewer for that paper.
Yeah, yeah, I guess that.
You could tell.
Yeah.
Very good. So, very good work, and I suppose we have 4 more minutes to start.
Yeah. Okay. So let me check.
Jose, you can ask Yanan to come in. Invite Yanan to come in. He wants to join in the Zoom group. Yes.
Yeah. There is another guy who initiated this research club with me, and we have a group of scientists, most of them young scientists, who we are doing this research. And now we have like more than 200 lectures this year.
So how long ago did you start this?
Since early March this year.
Good, exactly at the time of pandemic. Good.
Yeah.
I mean, almost end of pandemic in China, started pandemic everywhere else.
Yeah, but actually, students are still not allowed to go back to school at that time. Before,
yeah, how about now? You have all the university students back, am I right, on campus or not yet?
Yeah, except for some special areas like Xinjiang, they have a new instance there. They're not, but most of Chinese universities has probably recovered, at least 90% recovered.
Oh, good. Yeah, university is still closed. Research centers are open, but university for undergraduate students, bachelor students, they're all closed.
Okay, how about PhD students?
They're open, or PhDs open.
Okay, so are PhD students treated like as employees?
Exactly.
Okay. Actually, after your lecture, we will be collecting the questions from both sides. On Chinese side, we have a Bilibili platform. On YouTube, we'll be collecting questions for you to answer. Okay.
That will be long. Hopefully, I won't receive many questions, but then how should I answer these things?
I will give you some of questions so you can answer it. Anyway, just take it easy. I think it's a very thorough discussion on this very popular new research direction.
No problem. I'll see how I can cope with the questions. Hopefully, there are not many of them. Very good.
Okay. Okay. So, what's the length of your talk today? do you have some?
It's about 45, 50 minutes.
Okay, okay, I got it. So we are 1 minute away from the start.
Yep. Yeah.
Okay.
Hello, Professor.
Hello, how are you?
Yeah.
This is the other initiators of.
Oh, very good. So, Charles, where do you work?
Yeah, I'm in Beijing right now.
Okay,
and I'm also working Tianjin University. Yeah, and it's really our great honor to invite you to give us a talk today.
Thank you.
Yeah, just now I lost the internet, so I log in and out. I don't know. I log in again. Yeah.
Very good. Very good.
Hey, Shaya, is YouTube like okay? I saw the YouTube is on. Okay, probably it's time to start.
Yeah, we can do that.
Okay, let's begin. I'll start sharing. Good. Okay, let's start. Ladies and gentlemen, welcome to Research Clouds International. This is Shihu from Tianjin University, China, and one of the initiators of Research Clouds. Today, it is a very special day. First, it is Chinese Laureate Day, but more importantly, we are honored to have Professor Kourosh Kalantar-Zadeh from University of New South Wales with us. I believe a lot of Chinese laureates are watching this together. As you know, Professor Kalantar-Zadeh is a world-leading scientist in the field of liquid metals and electronics. He will be glad to share his knowledge and insight in his research field during this special day. I hope every one of you can enjoy his talk today, and we will have time for questions after his talk. Now, let me give a brief introduction of Professor Kalantar-Zadeh first. Kourosh Kalantar-Zadeh is a professor of chemical engineering at the University of New South Wales. He is one of the Australia Research Council Laureate Fellows of 2018. Professor Kalantar-Zadeh is involved in research in the fields of material science, electronics, and transducers. He has co-authored over 425 scientific papers and books, and is also a member of the editorial board of journals, including SS Sensors, SS Applied Nanomaterials, Advanced Materials Technologies, and SS Nano. He has received many international awards, including the 2017 IEEE Sensor Council Achievement, 2018 ACES Advances Environment Science Lectureship Award, and is also a 2020 IST Robert Boyle Prize for Analytical Science. His name also appeared in the Clarivate Analytics Most Highly Cited Scientist list since 2018. Today, he will give us a lecture on liquid metals for the synthesis of electronic materials. Now, let's welcome Professor Kourosh Kalantar-Zadeh.
Thank you very much, Dr. Hu. Okay, let me go to share. And Is this ready?
Yeah, we can play it.
Fine. All right, thank you very much. Thank you very much for the introduction. It's very kind of you. So today I'm going to talk about these liquid metals that in the past few years we worked on, we researched, and we used them for making different kinds of materials, including electronic materials. So what I am presenting today here, either about electrochemistry or electronics, are connected kind of to the field of electronics. So I started this work when I was at the previous institution. Then in 2018, moved to UNSW. So it's a work of my past group and my current group. And the work was funded by Australian Research Council. Okay. So what are these liquid metals? We have the famous ones like mercury, francium, cesium, gallium, and rubidium. They are kind of near room temperature. They are liquid, slightly above or beyond, below room temperature, but all of them at this around the room temperature kind of value. They are in liquid form. What does it mean? They are fluid. They are flexible. Other things that they can offer, they are highly thermally and electrically conductive, like any other metals. But the difference is that they can flow, they can alloy and mix with other metals. So that's the differentiation. Out of this family, mercury and gallium, they're researched a lot. Francium is radioactive, cesium and rubidium are explosive. So we put them aside. Unfortunately, mercury, against my opinion, I don't think that's hazardous. It's considered highly toxic. The mercury vapor is dangerous. It's dangerous for health, apparently. I remember when I was a child, I used to have a liter of mercury at home playing with it. And I think nothing happened to me, but it's another time. What remains out of this group is just gallium. Establishing a whole field based on one single element is very limiting. So what I did, I cheated. I put all post-transition metals into this group of liquid metals. And in order to be able to include them, I said any metal with a melting point of less than 330 degrees is included in this family. So it is, you see those blue metals in the table of elements: indium, tin, lead, thallium, and bismuth. Around them also you have other elements that can alloy into these metals, and you can make very interesting alloys. Let's go back to the main representative of this group, gallium. Melting point of gallium is around 30 degrees. Basically, you put it at the palm of your hand, it melts because our hand is 37, 36 degrees. It can alloy other metals at high volumes, like indium, tin, bismuth, and zinc. Two of the most famous alloys of gallium are gallium and EGAN. EGAN have 75% gallium, 25% indium. By adding indium, you increase the entropy of the alloy, and the melting point goes down to 15.7 degrees. The same, when you add tin, entropy even goes further down. Now, what makes it different, the gallium from mercury, is that gallium at the ambient condition, 21% oxygen around it, produces a very thin layer of gallium around this liquid metal. Mercury doesn't. So what's that? This layer is a two-dimensional oxide of gallium oxide. And like all other two-dimensional materials, it's kind of very strong across the plane. So as you see in this example by Michael Dickey at North Carolina University, they could print small droplets of liquid metal on the top of each other in this two-dimensional material, encapsulate these small droplets and hold them together to make them non-Newtonian structures, rather than very different from mercury, which always makes droplets which are round. Now, it can be observe this oxide? Yeah, it's very easy. Basically, you take one of these droplets, you start shaking it, the surface starts cracking this two-dimensional material. If you look at it under a scanning electron microscope, you see the wrinkles very similar to the wrinkles of graphene. You shake it more, they detach themselves from the surface because there is no adhesion to the liquid metal. Liquid metal is not polarized. So like any other liquid, doesn't show van der Waals forces. Comes off, they restack on the top of each other, and you can see this multi-layer restacked nanostructures. Today I'm going to talk about a few different topics that we worked on in my group, but the research on liquid metals is not limited to this. Basically, you can expand it to anything you can imagine. Liquid metals, like any other liquids, are solvents. You can use them as solvent to create things. But let's go to the topic of today. Today I'm going to talk about first non-crystalline nanoparticles. These are liquid metal nanoparticles. What are they? Basically, you take a bulk of liquid metal gallium, or even bismuth tin, you heat them up, you make them liquid, you sonicate them. So during the sonication, they break down into smaller particles, very similar to when you have oil and water together, they are immiscible. When you start shaking this oil and water into each other, you get droplets of oil into water. But the difference is oil, gradually those small droplets merge together, make the large droplet. Here, this thing doesn't happen because of the two-dimensional encapsulation of liquid metal gallium. It holds it together. So the more you shake, they become smaller, 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 and it makes a very stable suspension. You can drop cast them on an electrode. Here are two examples of how to make, for instance, heavy metal ion sensors, very similar to mercury. You can do voltammetry, stripping voltammetry, and it can swallow heavy metal ions like lead and cadmium into itself. Then you reverse the voltage, it comes out, you measure the current, is proportional to the concentration of this heavy metal ion. So basically, there are commercial heavy metal ion sensors based on this concept now deployed everywhere. So it's commercialized. Now, I'm talking about heterostructures. This is another concept, and it came from a very old time. I used to work on making two-dimensional materials like many other researchers, both in America and China. For instance, you may have heard about molybdenum disulfide. Deposition of molybdenum disulfide in 2 dimensions using chemical vapor deposition actually came from a lab. How does it work? You just heat them up. For instance, a precursor like molybdenum trioxide, you sulfurize it at the same time, and you produce these crystalline triangular crystals on the surface. So 2-dimensional, they're very thin. Unfortunately, the center of these triangular crystals is thick. Another unfortunate thing is the nucleation points are at different locations. So they start growing into these triangles, but the triangles, they go stitch into each other, or they grow on the top of each other. So you can never get a true 2-dimensional materials over a wafer size, wafer scale 2-dimensional material. That's a problem. You can use MB, you can use ALD, you have sort of more or less of the same nucleation problem on the surface. Of course, MB is less, but then it becomes very expensive. Now, how can we look at something better? Many years passed, there are commercial reactors based on this first paper that I published, but the reality is none of them is ideal. None of them can produce really continuous 2-dimensional material. Talking about liquid metals and the formation of the oxide on its surface, this oxide doesn't come from nucleation, but happens in the form of Mott-Cabrera oxidation, single crystal on the surface. It's atomically thin layer, one layer of this oxide. So basically anything that you don't achieve using vapor deposition or a liquid phase deposition technique, you obtain here. And you don't have those kind of stitching or growth of crystallized on top of each other. So you can melt gallium, indium, bismuth tin. They have low melting point. You can easily heat them up. in any lab, melt them. And what you can do, bring a substrate next to the surface, and this two-dimensional material, because it doesn't stick to liquid, sticks to the substrate, and you can harvest it. Here it is. Look at this example. This example of tin. Tin actually is not like gallium oxide. The oxide of tin is not self-limiting. It doesn't stop at only two-dimensional, very thin layer. It grows and grows and becomes thicker and thicker. The moment that it becomes thicker, the reflection of the color on the surface changes. It becomes yellow, red, and grayish blue. As you see these colors in this movie. You can take a piece of glass and very easily harvest them from the surface. As you see, this oxide sticks to the surface, oxide of this glass. You can bring a substrate to the surface, harvest them like SiO2 here on the surface. Here we melted tin, it produces tin monoxide, and you can harvest it again and again and again, and produce single layer of tin monoxide very quickly on the surface. It's very repeatable. You can do it by hand. Now, question is, can we give it a pattern? Can you produce pattern and make electronic devices out of this? Look at this example of how to make this pattern. Here we put photoresist on the substrate that you want to produce the pattern of this material. For instance, you use a mask, you expose the mask into the light passes through areas and it stops where you have the patterns in the mask, and it changes the property of photoresist. You can develop it, then you have areas of photoresist covering and areas with no photoresist covering after development. What we did here, we use a fluorinated material, fluoride containing material. We fluorinated the areas which are not covered, and we put a droplet of liquid gallium with the surface of oxide, and the surface is oxide. Stick to the surface. We take a squeegee, remove the metal from the surface. All right, something happened. Okay, wait. Can you hear me? I hope so. I'll continue. So then we can take a squeegee. Squeegee remove the liquid metal from the surface, and what remains is gallium oxide material, two-dimensional material on the surface. Now, gallium oxide is a very good material for making high-power transistors, whether we can use it like that, or you can do the transformation. For instance, here we sulfurize it in a two-step process. We expose it to HCl, produces gallium chloride. Then at low temperature, we expose it to sulfur. At under 300, we produces gallium sulfide. This gallium sulfide is a two-layer gallium sulfide is one unit cell. This two-layered one unit cell is the most stable structure of this gallium sulfide, 1.5 nanometers. Has a very good photoluminescence. As you see, it's homogeneous, even though that we put everything by hand. As you see, the stripes that we put in by hand, they have the same intensity, all of them the same. We made transistors I haven't presented here in these slides. You can take that gallium oxide and play with it and make other materials. Here is actually gallium phosphate. We wanted to produce gallium phosphide, but we couldn't. At the temperature that we use when you expose it to hydrogen phosphate vapor at 350 degrees, it transformed gallium oxide to gallium phosphate. We thought that was a failure, but serendipitously that was a good material because gallium phosphate is a wide bandgap piezoelectric material which can tolerate very high temperature and has many applications. Interestingly, the piezoelectric coupling coefficient of this material was 7.5, which was much higher than the bulk of gallium phosphate as well. So we did lots of measurements, and eventually commercially you can put this into silicon-based devices, sensors. For instance, in accident, for measuring the acceleration change, when it releases the protection, for instance, pillows that stop people from becoming injured, airbags, this kind of accelerator measurement systems can help. You can also change it to other materials, gallium oxide. Here we expose it to a precursor of nitrogen. At 800 degrees, temperature was high, and we obtained gallium nitride from that gallium oxide. It was slightly oxidized gallium nitride, but the band gap was very nice, 3.5. Mobility was very good, more than 20 cm square per volt second. As you see, it's very smooth, two-dimensional materials, highly crystalline. And as you may know, gallium nitride is a base of many LEDs, which are used in low energy consumption lights. They're used in many households. So perhaps most of you have this at home as well. So it's a new way of producing high quality gallium nitride with high mobility. You can also make other materials which are of very high commercial value. Have you heard about ITO glass? I'm sure your mobile phone, the touch screen, or many of the, for instance, your laptop screen, they have ITO glasses. They are conductive glasses which are also transparent. Here, the good thing is made of indium and tin. We know that both of them are in our family of liquid metals, melting point less than 330 degrees. We mix them together, they make alloys. Even the melting point goes smaller than indium and tin. But doesn't matter. In this case, we heated up everything at 200 degrees. We squeezed the melted droplet between two substrates, and the oxide goes on both sides. This oxide is transparent, as you see, and we characterize it one layer. You can repeat the deposition, 1 layer, 2 layer, 3 layers. It's super transparent. It's much more transparent than commercial ITO glasses that you buy in the market. We're talking about losing the light 1 or 2% only. Another important thing is made of two-dimensional crystal. It's a new crystal of ITO. It can be bent. It can be bent many million times without losing its integrity. The conductivity is very comparable with the commercial ITO glasses, even at 2 layers. Now, lots of interest in making that commercially and scaling up. Now, going to research again and see whether we can expand the field and idea. First of all, we realize materials like ITO, which are inherently not layered, we could layer the structure of this material. One, can we do it for other metals and metal oxides? Second, is it possible to go and also produce other metal, two-dimensional metals from the liquid metal that we have, and use different kinds of tricks, either from the core of liquid metal or surface of liquid metal? And we target transition metals, not just post-transition metals. So one of my postdocs at the time had a very interesting observation. He said, look, we have E-gain, we have gallium, that we have indium, and we have indium and tin inside gallium, but always gallium is the material that comes to the surface. Indium and tin, they don't go to the surface. So it was very interesting for me, as I was thinking, maybe there is a competition between the elements that we introduce into the liquid metals. And if so, if the secondary metal come to the surface and it get oxidized faster than gallium, then we can produce the two-dimensional material of these secondary materials. So we asked one of my students, he went and tried all different metals like hafnium, gadolinium, aluminium. He realized that hafnium, gadolinium, hafnium oxide, gadolinium oxide, aluminium oxide, they win the competition, they come to the surface. But on the other side, metals like copper, silver, tin, indium, they don't come to the surface to make the oxide. He came with the idea that, yeah, the oxide, the Gibbs free energy formation of the oxide of these materials, if it's more than gallium oxide, they lose the competition. If it's less, they come to the surface. Here are the materials. Look at that. Hafnium oxide, 0.6 nanometers. Hafnium oxide is the thinnest hafnium oxide ever made. Made devices with it. Actually, hafnium oxide is the base of electronics, the gate for electronics, silicon electronics. At the moment, the thinnest hafnium oxide used by chemical vapor deposition is 3-4 nanometers. Imagine to use this, you can reduce the on-off voltage for transistor, which reduces, it changes basically electronics, a new paradigm. You can make aluminum oxide very, very thin and very large dimensions. Here, look at the example of using aluminum oxide. Here, we put a droplet of liquid metal, gallium. We put 3.125% aluminum. Aluminum means the competition comes to the surface. If you immerse everything in water, hydrated aluminum oxide is produced, bohemite, and at the same time, hydrogen is produced. Hydrogen exfoliates very rapidly this bohemite two-dimensional material. The corners of them attach to each other. Basically, it makes a very nice hydrogel. You can dry it, or you can use it as it is and take them out, make some filters, and the spacing between these bohemite films, bohemite layers is very small, just nanometers. Oil doesn't pass through, and aluminum oxide is famous for absorbing heavy metal ions or other transition metals, many other ones. So basically, you can pass water from one side to another. You have dirty water full of contaminants on one side. The other side is perfectly pure water ready for drinking. Another example here, tin sulfide. Tin sulfide in 2015, a group at Michigan University predicted that this material can have a very high piezoelectric coupling coefficient, D11 of 144 picometer per volt. It's really gigantic. No one has been able to make it because the lone pair electron of sulfur in the layers of tin sulfide, they produce a much stronger force than the van der Waals forces between the layers. Okay, now, no one could exfoliate it using sticky tape or just simple sonication kind of exfoliation method. And we obtained this kind of very high piezoelectric coupling coefficient because of puckered shape. As you see, it looks like an accordion. They can stretch it, stretch it, stretch it. So we thought, what can we do? We thought, why not changing the environment from oxygen to H2S? H2S is even at very, very low concentration, interact very fast with the surface. It actually changed the tin oxide that was supposed to appear on the surface to tin sulfide in a glove box when we exfoliated. Very simple. As you see, we could put this on the TEM grid, a very nice piece which is there, even broken on the TEM grid. We look at different parts, and the crystallinity, as you see, the crystal, they have the same direction. All of them are highly crystalline. Is one layer 0.7 nanometers, and Raman measurements show that it's a perfect, very high quality tin sulfide. We did the electronic measurements, electron band gap of very low 1.4 electron volts is very nice, is comparable to that of silicon. The mobility was very high, 35 Siemens square per volt second, and the density of carriers were very high, and it's a p-type. P-type materials are very rare in two-dimensional with this high carrier mobility. We made devices, as you see, we put it on our finger. It produced 200 millivolts of voltage, very high. We did a measurement. It showed that the piezoelectric coupling coefficient is 220 picometer per volt. It's very high. It's much higher than most of the conventional materials. And this output voltage is also very high in comparison to any other two-dimensional material. So it's a record. We didn't reach the prediction that was supposed to be about 140, but the number still is very, very high. Now, can we use the surface of liquid metal for synthesizing other materials? The surface is mirror. Surface is very smooth, it's super smooth. Yes, liquid metals are highly reactive. Basically, here is an example. We put permanganate potassium, around it, and these manganate ions went to the surface and produced manganese oxide. This manganese will self-exfoliate, and in time becomes thicker and thicker, self-exfoliate. We get this fluff that comes out, and we can use it for many different applications. Saying that, and knowing that this material is very reactive, we thought, is there any possibility to basically produce graphitic type material on the surface? We did the DFT calculation. We realized, yeah, it's possible to break CH bonds on the surface, produce different kind of radicals, and these radicals also diffuse into the surface. They react, they make CC bond, and the CC bond cannot remain dissolved, come to the surface as two-dimensional material. We put electrochemical reactors. We tried many different precursors, from small size precursor like methanol, ethanol, to larger size. Then the precursors that have nitrogen in them, like acetonitrile and pyridine, and also some rings. And we did all the measurements. Look at this. When we don't have any fuel in the environment, no organic fuel, nothing is formed on the surface, you apply a voltage, it deforms the liquid metal. And when we have the precursor fuel, we have graphitic material formed on the surface at 0.7 volts. It's very, very small voltage. All right. We realize if we make the material more catalytic, that means we add more and more of a secondary, tertiary metal into the surface, the reaction happens faster. For instance, when we have tin, rather than nothing, or rather than having only indium and gallium, the reaction was happening faster. As you see, the current increased. Material is a two-dimensional material formed on the surface, but the Raman is not great. As you see, it's very broad. Look at the TEM and realize, okay, it's two-dimensional, but it's a super porous two-dimensional materials. Of course, we can use this two-dimensional material for making battery electrodes. We haven't done it. We can go and do it. It's extraordinary porous. But what we did, we wanted to obtain smooth graphitic material. Instead of letting liquid metal to move around, we painted liquid metal on the surface of an electrode here, surface of copper. We apply the voltage across. It is produced on a surface. The surface is not deformed, and because of self-exfoliation, exfoliate, and it goes to the other electrode using electrophoresis. As I say, the surface is smooth. You can make it multiple layer by increasing the voltage. And the interesting thing is you can have relatively high crystalline graphene oxide. Or when you use the pyridine, for instance, or acetonitrile, because you have nitrogen in the environment, you in situ dope the material during, with, for instance, nitrogen. During the synthesis, as you know, nitrogen-doped graphene oxide or graphene are highly catalytic material. Again, we didn't use it for making any, for instance, battery electrode. You can go and try it. Crystallization. I talked about surface of liquid metal a lot, but the core of liquid metal is also another magic. Here, look at the example. Cerium solubility in gallium is low. It's only 0.1, 0.2%. Here we added about 2-3% of cerium. So when you oversaturate this material, very similar when you oversaturate water with sugar, and you after a day you get crystal of sugar inside water forming around the glass. The same thing happened as well. We look at this small liquid metal crystals in TEM, high resolution TEM. We realize that we have crystals of cerium inside, and this crystal tend to come to the surface, push themselves against the cerium oxide surface, which is formed on the surface of gallium. So it's a very interesting, we call it a complex system, but it's a very interesting system that can be simply made in a kitchen. Now, we have cerium oxide, cerium 2 oxide 3, not highly oxidized cerium on the surface. And we bubble CO2, we put everything in an electrolyte, and we bubble CO2 around it. The CO2 comes and oxidizes this cerium, which was not a full stoichiometry cerium oxide. and make it CeO2, full stoichiometry, oxide of cerium. And we use it as an electrode, and we apply voltage to reduce it. So this continues this cycle. So carbon is produced from this reduction. Generally, in electrochemical conversion, when we use a solid surface, we don't want that because carbon becomes thicker and thicker. It stops the reaction. Here, we don't care. You have liquid metal. Carbon detaches, self-exfoliates itself from the surface, and it comes down. So we have done the characterization, and we realize that we can continuously, as you see, the current is continuous. Carbon flakes come off the surface constantly. We can produce carbon, slightly oxidized carbon from CO2. So it's like converting CO2 back to coal. The onset voltage for that was very small, only 0.3 volts. And as you see, Faradaic efficiency is very high, is about 80%. So it's an interesting thing. We're not limited to gas or liquid in the conversion. Now we can also go and challenge ourselves in producing lots of solid materials in this conversion if the electrode is liquid metal. Phase separation. Now we can go back to a little bit of classic liquid metals and classic metallurgy. Look, the bismuth melting point is about 271. Tin melting point is 232. You combine them together, mix them together, eutectic alloy of bismuth and tin at 57% bismuth, and the rest tin, the melting point reduces because entropy goes higher, is 139. It's relatively low. You can mix bismuth and tin at different concentrations of these two metals, make different alloys, including that eutectic alloy at 57%. And at 200 degrees, you can melt them all and produce these nanoparticles of bismuth and tin. You can use them as they are, as metallic nanoparticles with oxide on the surface, or anneal them further at 500 degrees, for instance, and oxidize the whole bulk of the nanoparticles that you make. Okay. You sonicate it for a few minutes, it remains relatively large, and you break some of these particles that you make. You see classical metallurgy. When you have bismuth at 20% and 80% tin, you see rods of bismuth into the crystal of tin, very highly ordered rods. Or when you have 80% of bismuth and 20% of tin, you see crisscross of metallic two-dimensional structures, crystals, as I mentioned, crisscross each other. So these are very interesting material because they're topological insulators. If you take those bismuth and tin out, you can use them for future electronics. Or you can look at the highly volatile eutectic alloys with the lowest melting point temperature, because the lowest entropy is the highest. When you solidify them, they don't have enough time to form into crystal. They make these fibrous structures, as you see. So it's fibrous, it's less crystalline, it's full of effects. Now, imagine you sonicate everything and you go from eutectic alloy to less eutectic alloys. What will happen? Now, if you don't shake everything and you take the exfoliation of only oxide from the surface of the bulk, what comes out is a competition between the tin and bismuth, and tin wins the competition. Tin monoxide comes out, and you exfoliate it. Now, you shake everything, suddenly thermodynamic of the system changes. You get bismuth oxide, you get tin oxide, and you get tin dioxide on the surface. Not only that, you get loss of line, surface defects, edge dislocation, and boundaries in the eutectic system, much more than the other systems. All right, what does it mean? You have nanoparticles, the surface is oxide, the core is less oxidized, more metallic, and it's full of defects on the surface. You can use it for traditional CO2 conversion in using electrochemical means. For instance, here we use it for producing formate, and we did all the characterization to realize that the best material was, in fact, eutectic system that the highest boundary, grain boundaries, highest defects, and produce the Faradaic efficiency of relatively high 78% for formate conversion at the onset voltage of 1.5 volts. This is the last page that I want to show you. Last slide is that you can then anneal everything, oxidize everything. Here, not only we had tin, indium, and bismuth, we also trying to add silver. We add silver directly alloyed, or we added using a silver salt to the system, so we could control the concentration of silver and also the formation of nanoparticles of silver on the surface. So we could make materials that have silver, have different concentrations of tin, indium, and bismuth. What does it do? Maybe as a general, it's not important, but by changing this material, basically cooking the material, we could make the material more or less selective to different pollutants. Here, examples of the pollutants are the degradation of the dyes, Congo red dye, methylene blue dye. We could make it more or less selective to photocatalysis of these dyes. So basically today, I just wanted to give you an overview of this field of liquid metals, what you can do. You can use liquid metal nanoparticles. They're very interesting, very volatile, very active, not volatile. You can use the crystallization, go to basic metallurgy, cool the system down, see how they separate, what is formed on the surface, what is formed in the bulk, and use them for different structures, for different applications. You can look at the two-dimensional material on the surface, harvest it, make electronics. Very cool electronics, P-type, N-type material at very low dimension, and phase separation. And you can use the core of the material. You can dissolve lots of secondary, tertiary elements and see how the secondary material crystalline in the surface. The reality is liquid metal is a solvent. You can always dissolve a secondary element, but here is a good solvent for other metals. Secondary metal into liquid metal and see what comes out. So I would like to thank our collaborators, both in Australia and America, and also I would like to thank my past and present group members one more time. And it's very important to thank the providers of the fund, which is a Laureate fellowship for me, and also the Center of Excellence in Future Low Energy Electronic Technology in Australia. And I would like to thank you for being here present and listening to my talk, and have the patience to go through this 45 minutes of talk. Thank you very much.
Thank you. And Professor, now we are now you can still share the slides. So
okay, I'll share it again. Okay, I'll share it again.
The questions, you can point to the pictures when needed.
Okay.
Yeah. So I have some questions on my hand. The first is
somehow the file is closed. Let me open it again.
Oh, never mind.
It comes back very soon. Okay, it's back. Yes. Yes, please.
Okay. So question one is, what is the effect of the concentration of oxygen in the formation of 2D oxide?
Okay, so basically, that's a very good question. I'll show you something. Do you remember I said that for gallium, right? then you expose it to 21% oxygen, ambient oxygen is 21%, right? It produces a self-limiting oxide that protects the core of gallium from further oxidation. That oxide doesn't become thicker and thicker for gallium. Okay, very similar to aluminum as well. Of course, aluminum is solid, but aluminum surface doesn't become thicker. It remains 1 or 2 nanometers of aluminum oxide on the surface of aluminum. However, for materials like bismuth and tin, this is very different. In ambient 21% oxygen, the oxide layer of tin or bismuth become thicker and thicker and thicker in time, and in 21%. If you want to go to the self-limiting scheme, then you have to reduce the oxygen in the environment. You can put everything in glove box, bring the oxygen to less than 1%, then it becomes self-limiting. It doesn't become thick. So exactly, apparently there is an equilibrium. Eventually it will reach. So the lower oxygen you have in the environment, or the lower, or the type of the material that you use, it defines and governs the property of the surface, whether it becomes continuously thicker or self-limiting oxide.
Okay. So there's another question here about why does the oxide on the liquid metal droplet feels sticky on hand or something?
Okay, so the oxide, if you have gallium, right? I had this discussion with you as well before to talk. When you have the gallium and put it in your hand, right? Because we have a layer, a very, very thin layer of oxide formed very quickly on the surface. This oxide has van der Waals forces, right? And the oxide itself sticks to the surface. Of course, this oxide encompasses, encircles the liquid metal. So it's like bringing metal oxide down to the surface. So the moment that you don't have that oxide, it becomes very similar to mercury. Actually, if you put your hand inside a glove box with nitrogen and a gallium rolls around without leaving any residues on the surface of your hand.
Okay. Okay. So another question about the formation of oxide on the surface of alloys, liquid alloys. So will there be any possibility that mixed to the oxide will be formed at the surface?
Is there any possibility to, would you please repeat?
To form mixed oxide rather than a preferential?
Look, that's a very good question. Let's go back to this slide, ITO glass. So perhaps I jumped through it very quickly. So ITO glass, we put indium and tin at different ratios. I didn't explain this one. It's very interesting because you have the alloy concentration, for instance, at 2%, 4%, 6%, right? The surface concentration of tin, bismuth, tin and indium is very different. So there is always a competition between the two materials that you put in the core. Depends on which one of them is going to the surface. Again, you can do the DFT calculation or molecular dynamic calculation. It shows one of them can go to the surface and enrich the surface more than the other one. So we don't know, right? It has been a kind of discussion for years and years. First of all, how they go to the surface, how they will enrich the surface, all these things. We are working on it. We have a new paper that should be published very soon about this.
Okay. There is another question similarly on this topic. So, because at the end of your science paper, you list all the thermodynamic data for different types of oxides. So I thought that data was based on the traditional bark data. So when 2D materials forms on the surface, how did you determine? Because when 2D materials form on the surface, the surface energy is also very important. So
you're right. You're right. Yeah. Look, You're right. I think our hypothesis, right? And of course, match the observation that we have done at the time is good, but it's very basic. The thermodynamic can change a lot, and that basic definition does not include many parameters that can change the surface and change the thermodynamic of the surface, right? For instance, I'll tell you, when even the simplest thing, when you have tin oxide, when you wait for a tin monoxide, when you wait for 2-3 minutes, that tin monoxide remains on the surface, but underneath we have the second layer of tin dioxide. So that table that we put in does not define the formation of the secondary layer. And if it does, what kind of a structure of a secondary layer we obtain? That's super basic. I think the whole world of this formation of this 2D material on the surface is very complicated, and many work and research and papers can be published in the future.
Yeah, I agree. Yeah, I was also interested in this topic and doing some research at the same time. And let me see if there's any other questions. Okay. And
hi, Professor. Can I ask a question?
Sure, definitely.
Yeah, okay. So first, thanks very much for your wonderful talk. This talk gives us a lot of inspiration. So I'm just curious if anyone investigates the application of liquid metal in the application as electrode material in battery, such as lithium-ion battery.
Yeah, look, actually there are very good papers. I think I cannot remember the name of the group. One of the papers that were published 2 years ago in Energy Environmental Science. It's a good journal. I think by combining liquid metal either with graphene or carbon nanotube, they reached a relatively high, almost a record for supercapacitor capacity. It was almost a record. So yeah, look, it's possible to use gallium as the battery electrode. Gallium can take two lithium can be combined with one gallium. So it has that much capacity for accept lithium. But when lithium goes into gallium, gradually solidifies it and increases the melting point. So when you're talking about a battery that accepts lithium, if you want to use a very high capacity for the battery, it's better to increase the temperature slightly above the room temperature. So there are a few things that you can do. It's liquid, it can accept, and it can dissolve lithium in itself. It can get mixed really nicely with, because this oxide of gallium actually helps a lot to attach itself to graphene or carbon nanotube. It's possible to do lots of very interesting, exciting things to make battery electrodes and supercapacitors, definitely.
Yeah, okay, thank you, Professor. Yeah, I think if successful, it will be a revolutionary technique for the electrode design for battery.
Yeah, sure.
Yes, thank you so much.
Thank you.
Okay, I think that's so much for the questions. Okay, and I think let's thank you again for today's wonderful talk and question answering. Okay.
Thank you very much. Thank you very much for organizing this.
Okay, so we will have a playback of today's video, and including the Q&A part on our YouTube and Chinese website. So, and if you allow us to do so. Okay.
Sure. Later on, I will talk to you about it, and hopefully I can answer more questions later.
Okay, that's great. So
thank you very much.
Thank you for today's talk, and also you are welcome to invite all your friends to come to us for another talk.
Sure. Definitely.
Okay, so that's all for today's talk. So I will have a 2 minutes mm, closing mark for today's show. And coming next is our next lectures on August 27th, and it will be given by Professor Xiongwei Wu from Hunan Agricultural University and Tan Wang from Tianjin University. And you're welcome to scan the QR code to join our WeChat group. And also, you're welcome to subscribe to our WeChat, Facebook, YouTube, and Twitter accounts for the latest research news and lecture notice. And that's all for today's show, and see you next time.